Okay, so your written test will be this coming Thursday during the lecture time, WSC, the same place, okay, within Small Center. I know that your emergency item should be get prepared for written test. I do agree, but assignment number 3, if you get something done, because the deadline, I believe, is approaching as well. It's participation based. You don't need to worry about losing marks, but for your learning, you want to get as much done as possible before the deadline. You don't want to just look at the solution, okay? That's all I can say. Assignment number 3, you want to get started with it. For the written test, you already got a guide, you got an example question. I'll maybe send you guys a reminder about the policy. Make sure you bring your ID, your mobile phone. You're going to need that for dual mobile. And there was a review session yesterday. I already posted a recording. The quality wasn't as good as it could be, but it's watchable. How about that? I'll improve it next time. We definitely got some more review sessions coming. And the makeup lecture that's going to be covered in Thursday's test, ADTs and stacks. And I still have my office hour tomorrow, 3 to 4 p.m. If you want to speak to me, you're more than welcome to. All right, guys, any questions about the course? All right, let's now do recap. Okay, and then we'll continue with the trees topic. Okay. So last time we really dived deep into the general structure of a binary tree by applying the geometrical sequence sum formula, right? So just don't forget, you got to do this exercise here about the height of the tree. You got a Java code, and also you got some JUnit test cases. You got to trace it up using the unfolding technique I showed to you, and then you can let me know if you got any trouble. There's also a solution video on the lecture site you can also look at. And we spoke about how you can think about algorithm recursively in 2 simple cases. We got counting the number of nodes. That's something we discussed already. And this one here is interesting. For this one here, the principle really is, if I want to start searching from this node here, the top of the tree, if A does not really match the G I'm looking for, I should go for the left subtree. If it's not there, I should also go to the right subtree. That means in the worst case, I may have to traverse the whole tree to really get the item found, right? However, towards the end of today, maybe in the second half, we're going to learn about a technique, like an algorithm called binary search. But to start with, I want to start with something a little bit more basic. We're going to do binary search on a linear sequence, like an array. But later on, I'm going to draw this particular connection about tree to binary search maybe next Tuesday once we get there, right? That's something you also need to know before you graduate from this course. Okay? But you can just remember, you don't necessarily have to always go to both the left and right subtree to search for some item if you're able to prepare the input in a certain format. That's something we'll talk about later. And we went through this page here from scratch about what's the maximum number of nodes at each level and how you add them up together using this formula here about geometrical sequence sum. You're going to need this formula for Thursday. And by the way, guys, for Thursday, no calculator. I'm going to also confirm that tomorrow. So if you can calculate by hands up to 2 to the power of 10, you should be fine. You do know what it is, right? 2 to the power of 10. 10 times 4? Okay. It'll be something very obvious to you. Don't worry. I'm not going to give you anything that's not going to be like a fractional number. For log, it'll be it's going to be log evenly. Okay. Again, no calculator on Thursday. But I can bring sketch paper, as many as you like. All right, and then we spoke about the difference between the complete versus full binary tree. All right, so you really want to know the difference. You want to look at the textual definition on the slides. There are 3 parts of them about complete binary tree. And then from there, you're going to understand about the visual intuition and then how we calculate the minimum versus the maximum for the full, complete binary tree. And in the case of full binary tree, minimum and maximum are just the same, right? That's something we said last time. You can review. And this one here, just a visual summary about the difference between the 2. You can also review them. And this one is just one example where it's not really a complete binary tree. And we talked about why last time. You can also review the reason. And we try to talk about different measures about the binary tree. There are 4 basic measures, basically. So number of nodes, also the heights, the number of internal nodes, and the number of external nodes. We have done half of them. We're going to do the other half to begin with today. So let's do very quickly. Given some particular heights of the tree, let's say h, You can now say the maximum height you can get will be 2 to the power of h plus 1 minus 1, and the minimum will be h plus 1. Of course, if you only look at the equation right away, it may not make much more sense. You really have to look at how we justify each case visually. That's going to help. If you've got any doubts, you should really refer to the lecture recording from Thursday last week. The second measure is about the height of the tree. This one is particularly important because whenever we talk about how high the tree is, it could be ranging between log n to linear. So how efficient your algorithm is really also depends on the tree structure you're given as input. That's something we'll emphasize a little bit more later. But for now, you're learning the basics. You just got to know whenever you got a fixed number of nodes in your tree, but depending on how the tree is going to be structured, the height could be very, very high, like a linear, or could be very, very short, like a log n. Okay, that's really the thing you want to know for now about the different bounds, lower bound and upper bound. And we talk about pre-order and post-order traversal. You really want to know how they work conceptually. We got some more like a pseudocode for you, close to Java code on the slide. You can take a look at the recursive definition, make sure you're able to follow the recursive definition and do the example that we did accordingly, right? So we did it pre-order and also post-order. We did both order on the family tree, and also we did it on this arithmetic expression tree, right? Pre-order or post-order. And I know I have left off this one thing here. So in-order traversal is covered on Thursday's test, but I'm going to make sure I go over this solution here with you, which will take me only 30 seconds, right? So that's something you're going to make sure. That's the only thing you're going to study for the written test, which I'm going to cover today. But what I'm going to cover today is also going to be very foundational. It might give you some inspiration for when you study for Thursday. We'll see. Okay, that's about what we covered from last Thursday. Any question? Any part you want me to explain again, or? All right, let's now continue. So what I would like to do is to continue with the bounds about the measure of binary tree. Number of nodes covered, height of tree also covered, 2 more. Let's talk about the number of internal versus external nodes. Let's start with the external node first. Okay, and you guys should really know the definition for external nodes for Thursday, right? Is any nodes without any child nodes. Okay? And what we can do is let's start with some example here and talk about what's the minimum, what's the maximum. So given some height h, you want to know given the h, for example, h can be 3. And let's remind ourselves very quickly, what's really h? H over here is really the maximum number of edges to go from the bottom node of the tree to the root, right? That's kind of intuitive meaning, maximum height, maximum depth basically for the bottom nodes. All right, let's say we got h equal to 3. What would be the way to really draw the tree so we got exactly we got exactly the minimum number of external nodes. Can the minimum be 0? If you think about it, there's no way you have 0 external nodes. Let's say you start with a single, if you got empty tree, of course you got 0. That one I agree. Okay? But if you actually got, let's say, 1 root over here, that's external, so it cannot be 0. If you got 2 nodes over here, you also got 1 external, also cannot be 0. So we talk about like a non-empty tree. Okay? So let's now try to see if I got height b equal to 3, how can I draw that? It turns out the only way for you to really get to the minimum number of external nodes is to keep 1 external node. So if I start with, let's say, this single node here, that's the root. If I got 1 edge over here, I still got 1 external node, right? Still 1. If I got another edge, I still got just 1 external node. If I got 1 more, which is the 3, I still got 1 external node. That's really the minimum you can get, which will be just 1. So think about this guy here is the only external nodes we have. External nodes. Whereas all the remaining nodes are internal. Okay, you can see that all these 3 are just internal. Because this node here has 1 child. This node here has 1 child, and this node here has 1 child, right? They are internal. And in general, we can generalize it right away. If you got, let's say, height h, what will be the tree that has the minimum number of external nodes? Exactly 1. So you want to think about this is the only external node we want to keep. And then we want to say we want to go all the way up to the root so that we got only 1 external node. Right? If we got 1, 2, 3, oh, let me just use this one here for you. Here you can see h is equal to 3. So that means we got 1, 2, and 3. We got 3 nodes in total over here, right? So if you got 3 edges as a maximum depth, you got exactly 1, 2, and 3 internal. They kind of match the number. So if I got h over here, how many internal nodes should I really get? H. All right? That's something you should really see the pattern. So here, the number of internal nodes over here, the number of internal nodes will just be equal to h. Again, if you see 1, 2, and 3, which correspond to just h3. And you only got 1 external nodes, right? The minimum. All right, so that's a minimum case. All right, any question about the minimum? We're good? Okay. And let's now try to do the maximum. Okay, the maximum, basically, the external node will be the nodes without any child nodes. You want to get as many of them as possible. You can think about visually, I want to put all the external nodes at the bottom level, right? So they are at the bottom level with no child nodes, basically. So let's say for h equals 3, I will still start with this minimum case first. 1, 2, and 3. That's a minimum case. In which case, I know that this is external. I want to create as many as I can while still maintaining the height to be 3. How can I do that? For example, I can add 1 more external node here. Height is still the same. I can add maybe another here and then another here. The height will still be the same. Right? You can see the pattern here, right? I want to add as many as I can. Okay, like that. Exactly that. It's a full binary tree. Right? So how many external nodes do we have? It's exactly what the formula tells you. It will be 2 to the h. And this one here should not be strange to you. That's one of the property that we spoke about last time. If you got h over here, what would be the maximum number of nodes at level h? It's exactly 2 to the h. So 2 to the 3, which is 8. Right? If you want some reminder, think about this is the level where d is equal to 0, d is equal to 1, d is equal to 2, and the bottom level is d equals 3. Okay, quick reminder. How do we generalize this? We basically just want to have a full binary tree of heights h. So what I will do is I'm going to draw this binary tree over here that's full binary tree of heights h. Right here. And then if I talk about the bottom layer here, all the nodes here should be external. They have no child nodes. Right? How many do we have? Exactly 2 to the h. All right? So that's a general case. All right, any question about this? Okay, just give me one moment. Let me just get it. Okay, good. Yeah, lower bound will be 1. Upper bound will be exactly the bottom layer. Okay? All right, and then let's now try to look at the bounds for internal nodes. Okay, let's see how they can be understood. So here we got h and then 2 to the h minus 1. But let's see exactly how that can be understood. The diagram turned out to be the same. Whatever that's really minimum for external is also the minimum for internal. Whatever that's really the minimum for external, whatever that's maximum for the external is also the maximum for the external. Turn out to be the same. Okay? Because they somehow complement to each other. Because all the remaining nodes are simply just internal if the only one there is external, and etc. All right, let's talk about the minimum case over here. So we're going to draw the same diagram here, and let's double check the formula. So when h is equal to 3, so we got a root over here, 1, 2, and 3. All the internal nodes are here, except for the bottom one. And the number of internal nodes will just correspond to the number of edges, the maximum number of edges, just 3. Okay? So here you can see the number of internal nodes will just be equal to 3. And the 3 here is exactly equal to h, the maximum number of edges that will go from the bottom to the root. General case will be, we're just going to draw a little bit more. Starting from the root, and then go all the way down to, let's say, right here. Okay? So internal nodes are exactly all these except for the bottom. Right? General case will be, if you think about, first of all, how many edges do I have? 1, 2, all the way to this bottom here. Given that the height is h, so I know that we got h edges. Since we got h edges, so we know that we got the number of internal nodes will just be h internal nodes. All right, any question? You just got to observe the pattern, right? You want to really be clear about the relationship between the number of edges, the number of external nodes, the number of internal nodes, or the number of nodes in general, right? Okay, let's see the maximum. Let's say in the case of h equals 3. So we're going to draw that complete binary tree again. So that'll be the same case. So start with this. So level 1, level 2, level 3. Right? That's height 3. And then all the internal nodes are here. Okay, we got exactly 7. Of course, you can count this in this simple example. But how do you, let's double check the formula before we make it general. If you want to check the formula, you can simply say, okay, this part over here is exactly, so the h, let me just remind you, the h is actually equal to 3. And then according to the formula, the maximum number of internal nodes would be 2 to the h minus 1, which will be 7. So that's matching 1, 2, 3, 4, 5, 6, 7. So it works on this small example. But how do you see that in the general case where the height is simply h, which can be arbitrarily small or large? So the way to see that would be, let's see here. So you got this general binary tree. And then the height is simply h, right here. Okay. And then we know that in the maximum case, we got all the external nodes at the bottom level, right? So these are all the external nodes, which we learned in the previous page. So what we want to focus on is about the internal nodes. Internal nodes will be exactly right here, just this part here. Okay, right this part. So this part here should be completely full. But how do we know how many nodes are there? We should really compute. So level 0, level 1, all the way to level h minus 1, right? Right, like a second last level from the bottom. So number of nodes will be 2 to the 0, 2 to the 1, plus all the way to 2 to the h minus 1. And then we can use our formula, right? If you just remind yourselves, sk would be 2 to the k minus 1. K here will be the number of terms. How many terms do we have? We got from 0 all the way to h minus 1. H terms, right? If you think that's right, that's good. So 2 to the h minus 1. So that's exactly what you saw right here. That's where it comes from. So you can see the way we kind of understand internal node, external node, they're kind of very complementary, right? So if you understand one, you should be able to understand the other. All right, any question? Okay, so these 2 pages are more like a warm-up for us. They are pretty much the same as how we discussed the other 2 measures last time. But what I would like to do today is something a little bit more deeper into the property for binary tree. So let's go back to the slides and I'll talk about this one here. We're going to do a little bit proof today. So we talk about bounding number of external nodes. We talk about bounding the number of internal nodes. let me introduce one more term, and then we'll do some mathematical induction. Mathematical induction turned out to be very natural for proving properties on a tree because the tree structure is recursive. And mathematical induction itself is also recursive, right? You got to make that mathematical, like an inductive hypothesis, right? So that's really about recursive idea, but we're going to get there, okay? So we have a new kind of tree called proper binary tree. What does it really mean for a binary tree to be proper? And the definition is very simple. It says that each internal node in the binary tree has exactly 2 children. Okay, that's a definition. Let's see how we can visualize this, right? So don't worry too much about this just yet. We'll get there. Let's try to see why this tree over here is proper. It's a binary tree, okay? But why is that proper? You have to look at each internal nodes. Let's identify the internal nodes first. This is internal, 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 and also internal. And external, I'm going to use the pink. External, external, external. External, external, external. Right? For externals, we don't care. They simply have no children. For internal, 2 children. 2. And also 2, also 2, and also 2. So that's a proper binary tree. How can I make this tree not proper? For example, if I simply get rid of this branch over here, in that way, this internal node has only 1 child. So that's not proper. All right? So that's a definition. So given this definition here, we want to prove a property about proper binary tree. Okay, let's now go over the property we want to prove, and I'll go step by step with you. It's a very common pattern that you might need, maybe not necessarily for the written test because today it's not really covered on Thursday, but it's actually going to be needed maybe for the exam. So you want to really get used to the pattern about using mathematical induction on tree. Okay, we'll go very slowly on this part. Okay, so let's go over the property. Let's say you're given a binary tree, and the tree is assumed to be not empty, at least 1 node, the root. So we'll start with that as a base case. And it's a proper binary tree. That means we assume every internal node has exactly 2 children. Okay, so these are the 2 properties for the input. When you think about it, it's like a precondition. And we're going to introduce 2 notation, Ni and Ne. I'm going to write here. I'm going to write N with a subscript I. So that'll be the number of internal nodes. For example, the number of internal nodes right here would be 1, 2, 3, 4, 5. Right? And then we got also another Ne right here. Ne will be the number of external nodes. In this case, Ne will be, you can see, 1, 2, 3, 4, 5, 6. Right? Simple notation. Later on, we're going to create a different version about these 2 variables, which we'll get into in order to prove our property. We'll get to it in the middle of the proof. So this is the property that we want to actually prove. Okay? For any given binary tree that's not empty and proper, the number of external nodes will be exactly equal to the number of internal nodes plus 1. Just 1 more. Okay? That's a property. Which may or may not sound intuitive to you, but we're going to prove it mathematically. Let's now double check this formula here in this tree. So we already got Ni, we already got Ne. Ne in this case is 6, which is equal to 5 plus 1. So it works on this small proper binary tree. Okay? So what I really want to do now is to really make this general by proving it. Okay? So what you guys really want to see in the next maybe 15 to 20 minutes is as follows. It's going to be challenging. You might just get lost, but hang on. Okay? Based on my observation from your fellow student from the morning. Okay? Let me give you some idea. You want to focus more on thinking about a binary tree in a very abstract way about its shape, and think about how you can somehow extend it to the least amount of extent and see how you can prove the property accordingly. So let's say, for example, let's do some warm-up exercise. If this is my proper binary tree, how can I make it slightly bigger? If I want to make it bigger, guys, how many nodes should I add? Why can I not just add 1 node? Because if you add 1 node, it's not going to be proper anymore. Aha, very good, exactly. What Diego said exactly right. If I want to make the tree bigger, if I just add 0 node, doesn't make sense. It's not bigger. If I add 1 node, let's say here, it's not proper anymore. I need to add minimum 2 nodes to make it bigger. So this is a very important insight when you want to apply the inductive hypothesis. Right? Keep this insight in mind. All right, let's now get started. Let me give you an idea. We're going to get 1, 2, 3, 4. We're going to get 4 steps in total. Step number 1, we're going to talk about base case, which is very straightforward. I'm going to show it to you. And then we're going to talk about inductive hypothesis, just stated. Number 3, we're going to talk about, in general, how can you extend the proper binary tree by just the least extent, which I already showed you the insight. Step number 3. Step number 4, we're going to apply everything together to show that. All right, 4 steps. Step number 1. So, base case. So the base case will be, usually for the base case of a tree, you will start with empty tree, but we assume it's not empty, so it cannot be empty. One singleton tree. So I would say it's a singleton proper binary tree. How do I visualize it? Well, just one node. Agree? Exactly, just one node. Guys, by the way, why is this tree actually proper? The proper binary tree, actually, oh, Diego, go ahead. You can go.
I think it will be because there's only one external node and no internal nodes, because it has no...
Yeah, exactly. We don't care about anything about external. It's just by itself. If there's any internal, we make sure it has exactly 2 children. Since there's no internal nodes in this case, there's no way to violate the property. Right? So this is a proper binary tree in the least amount of nodes. All right, so what we're going to do is the number of external nodes is exactly equal to 1. And the number of internal nodes is equal to 0. And if you check the property here, 1 equals 0 plus 1. Base case proved. Step number 1 completed. All right. So we can say that the property holds. Okay, that's step number 1. Start with the base case. And let me remind you, in this particular proper binary tree problem here, the base case happened to be 1, but usually it could be 0, right? Depends on the problem. Okay, step number 2. Let's state the inductive hypothesis. It's more like a recursive call we can apply later. Inductive hypothesis simply means if we got any tree that's bigger than the base case, then this property here must hold, right? That's what you guys learned in the earlier math course. So step number 2, I'm going to write the inductive hypothesis. Inductive hypothesis. And I'm going to call that IH, which we can apply later. Okay, we're going to say for a proper binary tree, a proper binary tree of size cannot be the base case anymore, larger than 1. Must be at least 2 nodes. Okay? And we must have the property exactly here. Number of external nodes should be equal to number of internal nodes plus 1. And step number 2, done. Okay? Let me just color that just so that you can see. So number of external nodes will be right here. Number of internal nodes is right here. Okay, step number 2. Now, here comes the most difficult part, step number 3. We now want to think about the proper binary tree in a more abstract way, not like the concrete example anymore, because this one here is not general enough. But that one there does give us some very good idea. Okay, so what I will do is step number 3. Let me write down some text and then I'll visualize it for you. Let's say we're given some general proper binary tree. Given a proper binary tree like that, of certain size, and the size is strictly larger than 1. Okay? How can we extend it? Well, we're going to apply the insight as you guys kind of heard before. We got to choose one external node and then convert that into an internal node. That's the least amount of extension we can do. Now, which external should we choose? You can simply say, I can go to the rightmost external nodes. That's OK. Or you want to go to leftmost, doesn't matter. Let's say we'll go to rightmost. And the rightmost might just be here. All right? So we're just going to choose some external nodes right here. Let me call this external node N. I'm going to write it down, right? I want to visualize first. And then I'm going to convert that external node into internal nodes by adding 2 child nodes to it. So I'm going to get X and also Y. Think about this is X, this is Y. So think about N. Before the extension, N used to be external. After the extension, N has become internal. So there is certain change about the number of external nodes and number of internal nodes somehow. We've got to work it out exactly. We'll get there. Okay. So let me now complete the text over here. Given some proper binary tree, you want to extend it by choosing the rightmost external node, and let me just call that N right here. Okay. And adding and converting it to an internal node with child nodes X and Y. All right, so the X and Y right here. Okay, right here. Okay, so far? All right. So this part here is very important. So somehow we are trying to say, well, given a tree, in which case we can simply apply the inductive hypothesis. If we try to make some extension, we want to see, can we still use the inductive hypothesis to argue about after the extension? Can the number of external nodes that's being updated still be the number of internal nodes updated plus 1? That's the roadmap we're going. Okay? But let me introduce 2 more notation. Okay? What we used to get is Ni. I'm going to introduce something called Ni prime. Okay? Another one I'm going to write will be Ne prime. So the difference goes like this. Think about these 2 numbers are the internal node and external node before the extension. Before the extension, right? Before we added these 2 nodes, basically, okay? And think about these 2 notations are the one after the extension. After the extension, we got to consider N, X, and Y, right? So now we're going to play with these 4 variables to see how they relate to each other. It's not too bad, okay? And let me now just make some space for myself. I'm just going to make this guy smaller. All right, let's now talk about Ne prime and Ni prime. Let me start with Ne prime. Equals. Okay, let's start with that. If you think about it, what's happening is this. N used to be an external node before the extension. But after the extension, N is no longer external. Agree? So that means we should really get minus 1 on the external node side, just for N itself. Let's talk about node by node. So you're going to say whatever the number of external node is, minus 1. And the minus 1 here is really about the N being converted into internal. So this is really the N. However, on the bright side, after the extension, we got 2 external nodes, X and Y. So we're going to say plus 2. All right? And the plus 2 over here is really the X and Y. right? You can see here what you're doing here, right? We kind of say -1 plus 2, which of course end up being just +1. But I'd rather not write +1 right away. I want to show you the steps over here. Let me say that again. This number here represents the number of external nodes before the extension. And this one after the extension. Before the extension, from there, we're going to convert n from external into internal. So that's why the -1. And then we're adding these two nodes that are external. So that's why +2. Okay? If you simplify it, it's going to be NE plus 1. And let me call this guy here equation 1. We need one more. Okay? And for equation number 2, we're going to calculate Ni prime, which would be somehow very similar. Ni prime. Okay? Before the extension, n is external. After the extension, n has been converted into internal. So we're basically adding one more node. That's internal. Right? So it's going to be Ni plus 1. And the plus 1 here is exactly the n that we have converted into internal. So if you look at this part over here, -1 and +1, that reflects about the n being converted from external into internal. And for x and y, do we need to care? Not really. They're just external. So we don't need to worry about them for internal case, right? So we're done for equation 2. If you're following so far, that's great. That's the most complicated step. Okay? So what's really left is we got very nice abstract thinking done here, but we still don't know whether this property here will hold. We don't know. What we really want to show is over here, and we're going to show it. What we really want to show is after the extension, Ne, which is Ne prime, is equal to Ni after the extension, Ni prime plus 1. This is our goal. We haven't achieved that just yet, but we got all the necessary equations for us. Let's do that. That'll be step number 4, the final step. All right, let's now do the final step. We want to show that this equation here is going to be the case. Okay? So I'm just going to show to you step number 4. Right here. Oh, let me make it a little bit bigger. Okay, step number 4 is right here. So we want to show this particular equation. Let's start with Ne prime. Okay? Ne prime, the number of external nodes after the extension, which should be equal to, and first of all, let's apply equation 1. All right? So if you do equation 1, it's going to give you Ne plus 1. And then you can see we got Ne here. Remember hypothesis, inductive hypothesis, you say Ne equals Ni plus 1. Right? We can use that. And then you can say it's equal to by step number 2. And then I can say Ne here is exactly Ni plus 1. Ni plus 1 and then plus 1. All right? And don't simplify just yet. You can see Ni plus 1 is exactly Ni prime. Equation 2. Then I'm going to get equation 2. Oh, I beg your pardon. This one should be inductive hypothesis. Let me say it again. I do apologize. That's my fault. Okay. Let me say it again. When you go from here to here, I'm basically applying the inductive hypothesis. Ne is simply replaced by Ni plus 1, right? That's inductive hypothesis. Okay. And then Ni plus 1 is exactly equal to Mi prime, right? That's equation 2. Ni prime plus 1. What have we got? We got exactly Ne prime equals Ni prime plus 1, which is exactly this property here. So now we have proved that before and after the extension, doesn't matter how much extension you might do, it will always be a proper binary tree. And the property always holds. Okay, 4 steps. So what you really want to study for from this proof over here, this might be the only proof we'll do on the binary tree for this course. But I think that one that really shows to you, you want to have the base case inductive hypothesis to talk about a property, and then do some abstract manipulation of the tree, and then you want to show that the extended part of the extended version of the tree also satisfy the property, right? That's the pattern you want to see. Okay. All right, any question about this? Go ahead.
What if you would choose the leftmost external node instead of rightmost?
It will be the same, really. So the question was, let's say rather than choosing here, so let's say we don't have this, let's say, okay? If I choose the leftmost external nodes, it will be the same. Let me call it n, and then I can still get x and y. The math will still work. As long as you just choose one external node, it's just easier for me to identify where it is. We can simply say I choose an arbitrary external node. That's fine too. Yeah. Depends on how you phrase it. All right, pretty good. Let me do 2 more things that are pretty slight, and then we'll take a short break. Okay? And then we can move on to a new topic. Okay. All right, so we got proper binary tree cover, and we got the property proved, which is good. And then let's now talk about, okay, so this slide here just something called decision tree. It's just a proper binary tree application. This one here, very straightforward. If you look at the tree here, okay, I don't need to go any further. Okay, so here. Basically, every internal node over here, for example, are you nervous? That's more like a yes or no question, because there's only 2 possible answers, either yes or no, nothing in between. So every time from the internal node, you always branch out exactly 2 children. So that's why it's a proper binary tree. So decision tree is actually quite a useful data structure. For example, if you want to train your machine learning model, decision tree is one of the training model. Okay? For those of you who might be interested in machine learning, that's something you will learn. Of course, we'll just give you one example. It's a proper binary tree, because for every internal node, you got only 2 possible answers, either yes or no. And application 2 is about infix arithmetic expression. In the example question I gave to you for written test, I gave you something called postfix notation. So this one here, infix notation. So you kind of learn both. Okay. So the expression tree we have is here. I'm going to say a little bit more, and then I could ask you guys some question. There we go. All right. So that's the expression tree. And in this kind of expression tree here, we got external and internal. Let's talk about external first. So these are the external nodes without any children. Okay? So these are basically all the nodes representing the numerical constant, some numerical value we can operate. So here you can think about the external nodes are the numerical constants. On the other hand, the rest of the nodes are internal. Okay, all these. Each internal node simply represents an operation, binary operation to be more precise in this case, right? So all the internal nodes represent some binary numerical operation. Binary numerical operations. Let me give you some example. If you think about just this subtree here, this one represents the expression 3 plus 1. This part over here represents the 3 plus 1, which is this subtree here, multiply 3, and etc. Okay, that's how you interpret the tree. Remember, guys, I talked about compiler in the beginning of the course. If you want to implement compiler, that's kind of the tree you want to deal with all the time, okay? To really evaluate the tree or to traverse the tree to get something useful. But as far as for this course is concerned, this is enough, okay? But I do have one question for you, okay? You can see for this particular expression tree here, it happens to be proper. Now the question is, in general, if you actually want to use a binary tree to store arithmetic expression, does it really have to be binary? Does it really have to be proper? Can it be not proper? What I want you to think about is, what kind of arithmetic expression can I create to evaluate is it possible to include certain operations so the tree is not necessarily proper anymore?
Negation?
Negation, that's exactly right. If you think about a negation operator, like a negative, it's a unary operator, in which case you got only one child, which will make the tree not proper anymore. Okay, I'm going to write it down. Very good. Okay, so let me show you one example here. Let's say if I got, let's say, -5 multiplied by 4. How do I express this in a tree? Overall, it's more like a multiplication. So I'll start with multiplication, which has 2 children. Operand number 1, operand number 2. So 4 here, and then for operand number 1 here, it's more like a negation. So it's more like a negative. Below that, you got only one child node. 5. Okay, if you look at this tree here, it is binary. You can see you got at most 2 child, at most 2 children, but it's not proper. Okay. So this one here is a binary tree, but not proper. So if you want to include numeric, like a unary operator, then it cannot be proper. Okay, that's the point. Whether you want to keep it proper or not, it depends on your application. All right, one more thing, and then we'll take a short break. I want to complete the exercise that we're supposed to do from last time about in-order traversal. So if you go to the next slide, we went over already, 39, about traversal. And then if you look at, we talk about pre-order, post-order, give you a reminder for Thursday. Okay? Pre-order, post-order, you have no assumption about whether the tree should be general or binary. Any tree, you should be able to do pre-order, post-order. However, for in-order traversal, there is a strict precondition. The tree must be binary. You cannot do in-order traversal on a general tree with more than 2 nodes. You just cannot. More than 2 child nodes. And here's the rule. You're going to visit the parent node in the middle. Before that, you have to recursively visit the left child. And then after visiting the parents, you got to recursively visit the right child. So that's the rule. Okay? Let's see exactly how this will work very quickly. Right? And then we'll take a short break. So you can see here, we got in-order traversal. Okay? So what I will do is, I will try to recursively visit left subtree right here, followed by the root. Oh, let me use a different color. Followed by the root. And then I'm going to recursively visit the right subtree. That's the rule. Okay, of course, you can go further and further. And what's going to be the result for the pink one? It's going to be 3 plus 1 multiplied by 3 divided by 9 minus 5 plus 2. Okay? You guys got to practice to really apply that recursive definition on the slide to see how you can come up with this sequence. Right? That's kind of up to your practice. So that's the left subtree. And then we got a minus in the middle. And then we got to recursively do in-order traversal on the right subtree. Okay? That one there is going to be 3 multiplied 7 minus 4 plus 6. Okay, done. Yeah, so now you got 2 sets of complete example of doing pre-order and post-order, right? You can feel free to modify the expression tree yourself and try to see what the corresponding order should be, right? That's how you can practice. But if you already got a principle, you should be good. Okay. Well, any question? So we are now done with the trees lecture. All right. We're done with all of them. Just a little bit more example here. You can take a look. Okay. At the end of the slides. Okay, we're done. All right. If you know further question, why don't we take a short break and then we're gonna take attendance first, and then we'll continue. So we are now done with the trees lecture. So now I would like to take a little bit diversion from where we are. So we're going to continue with the tree topic with the binary search tree, most likely maybe about a week from now. So we don't have any lecture on Thursday, by the way. You guys got something more fun on Thursday, I'm pretty sure. And then I'm going to give you the makeup lecture to follow. It will be about a queue. And then next Tuesday, we're going to continue with the normal lecture. Okay. And for the makeup lecture, by the way, you can plan your time. There's no pressure to really finish that right away. It's not exactly related to what we're going to cover in the class. I want to make it that way so you can plan your time. As long as you can finish that makeup lecture by the exam, I'll be happy. Okay? All right, so now let's talk about some recursion here. I want to talk about, it's like a part 2. In part 1, we'll talk about some basics. In part 2, we're going to go a little bit deeper into recursion, especially how we can figure out their running time. That's something we'll do. We may not touch upon the running time today, but I'll definitely do that on Tuesday. So let's see the roadmap for this lecture here. So we're going to talk about recursive algorithm. I'll call it a little bit more intermediate. They do require more insight into what's the running time and also what's the code structure, right? We'll talk about it one by one. The simpler one we're going to talk about today is called binary search. You may have heard about it before, but what exactly it is, we're going to see. So binary search is one, and then we're going to talk about merge sort and quick sort. Okay, that'll be for next week when we come back from your test. All right, binary search. Let me just go over a little bit background, okay, quickly, and then we'll turn into iPad. Today, I'm mainly just going to talk about some intuition behind the binary search, how you can safely drop half of the search space, which will make more sense to you once I draw the diagram to you, okay? And then I'm going to look at maybe some Java code. And then we do the tracing. No, not yet. Haven't switched yet. Question? Yeah, is this going to be like included in Thursday? No. No. Do you want it to be included? I can do that? No. Okay, fine. Good. No, not included. I already clarified that, right? So no. Okay. So binary search is actually, let's go over some search problem here. So that's a computational problem. So this is very important, the precondition. Okay? If you want to perform binary search on a linear structure, the array, let's say, or linked list, let's say array, it must be sorted. Okay? If it is not sorted, whatever we're going to talk about on binary search is not going to work. That's a precondition. And the postcondition is you're going to say either true or false, whether some value what you're searching for is there, true or false. What if the precondition is not satisfied? In that way, you're basically back to 1021 or 1022. If you're given some arbitrary array, how do you get to see whether the element exists there? You just want to loop. The worst case, you go all the way until the end and find that there's no such thing in the array. So that'll be, worst case, linear time. However, as you will see today, a little bit intuitive sense, if we are able to get the inputs to be sorted first, and we perform the binary search, we will be able to achieve like a log n time, which is substantially better than linear time. Okay? That's something we'll see. And then a little bit look ahead. Next Tuesday or so, I'm also going to try to connect the way we perform binary search on a sorted array is very similar to how we perform binary search on a binary search tree. Right? That's something we also see later. So these are the two search contexts. They really work the same way. That's something you also got to see. All right, let's now talk about some idea. Have you guys ever used a hard copy dictionary? Oh, that's good. At least some people here are using it. Because I asked your fellow student in the morning, nobody has used it before. They may not have even seen that. At least that's what they thought. What they said to me. Anyway, I think to really understand binary search, you really want to think about some real-life example, like a dictionary. You can check it out in the library. I do have some dictionary in my office. You can feel free to come by and see how that works. Okay? But it's really the best way to see it. Let me describe it first. A dictionary is more like a book, maybe 1,000 pages. The way they organize the pages from front to the bottom is by sort all the English words in the alphabetic order, from A to Z. Okay? So there's some sorting going on in the book. Let's now visualize that a little bit, more like a linear structure. So we got our book over here, dictionary. Okay? It's going to sort from A all the way to Z. Okay? And you got 8 different English words. And then, for example, in the middle, you may have some K. And maybe somewhere in the middle here, you also got W, right? Etc. Right? You got different English words. Okay? Lots of English words there. Let's say I want to look up to see if they contain the definition for, let's say, Oxford, I want to see if this word actually exists over there. So what I normally do for the most efficient search, because I know the book is sorted alphabetically, I can definitely turn to the middle of the page. I can open the book and turn to the middle. Okay? When I turn to the middle, I see some English word starting from K, let's say. I look at the K here. I try to compare, for example, K versus the first letter right here. And then I want to somehow compare them to see which one is larger or smaller. In the English word, should O come before or after K? After. That means I can safely assume if the word Oxford does exist in the book, it must be after K. Here, I can safely disregard. That's a very critical step for doing binary search. Okay, let me visualize it and then we'll see. So I know that this part here is the only part I know is going to contain the English word Oxford, because I know that the O here is larger than K in some way. So it should come after the K. And this part over here, I can safely disregard. What's happening here is I started with searching the whole dictionary. And then after seeing what's really in the middle, I will be able to say, now I don't need to search the entire thing. I can only search half of it. I'm halving the search space each time. That's really the critical insight into binary search. All right. Let me go a little bit, one more step. And then I got this half of the book. Now I turn the other half again into half. So I'll get to W. Okay. So once I get to W, I want to compare to see the O here and the W here. I know that O should come before W. Agree? That means if the Oxford word really exists, it should be existing right here. Whereas this part over here, I can safely disregard. So what I have done is I cut down the search space twice. I started with the entire dictionary, and I decided that I can only focus on 50% of them. And then after looking at the middle part over here, I decided that I can only look at the 25% of them, and etc. 50%, 25%, 12.5%, etc. Each time I have the search space. That's really some step you have to keep doing until you find a word. If you never find a word and you find that there's no search space for you, then you just return false. Okay, that's really how it works intuitively. And let me say one more thing, and then we can try to do the similar thing again, but in an array that you're more familiar with. Okay. So let's talk about search space. So the size of the search space. Right here. Okay. So we start with the entire dictionary, which is N. After we have cut down the half of them, we only focus on here. That's second search space, N over 2, right? And then once we have seen this middle word again, we cut down another half. We cut down the half of N over 2, which is N over 4. Okay? And then we get to N over 4. So this pattern here is going to go on until, in the worst case, we have to go until the search space has only one element left for us to search. In which case, we can just compare if that one element in the search space matches the K we're looking for, right? Now the question is, what's the worst case number of searches we have to do? How many steps? How many steps would it take you to really go from N all the way to 1? And we know that each step is going to have the value of the previous value. Not n log n. You kind of get it on the right track, right? It's log n, okay, that's okay, but we're going to see exactly where the log n comes from. From today, I'm just telling you it should be log n, but we're going to see exactly how that log n will come out, okay? It's also important for you to know exactly how log n can be derived. But for today, I'm just giving you the facts. So the number of, so each time when you go to, let's say some middle, you want to compare the search word and also the word that's already there, right? You're going to do this many comparison. The number of comparison maximum will be log n. That's the worst case, as we shall see later. Okay, that's an important insight, which we're going to derive next time on Tuesday. All right, so let's now try to kind of wrap up everything with some little bit of repetition to talk about how the binary search is going to work on a linear collection. Let's look at it one more time. Okay. So think about this is the initial search space, entire array that we start with. So this is the initial search space. Of size n, a.length basically. Okay, that's a search space in the beginning. What we do is we want to know whether or not the value k exists in this entire array. What we do is we don't start from the beginning. We don't start from the end. We start from the middle. We're going to calculate where exactly the middle is. So the way to calculate is the index here, take the average. That'll be the middle part, right? That's the index you can do. Of course, if the number cannot really divide properly, you can take the ceiling or the floor, as long as you're consistent. That'll be okay. So what we want to do is we want to somehow take this middle value right here and then compare that against the value we are searching for, called k. So let's say this value over here is v. That's a middle value. We want, I'll put it here, middle value. And we want to compare this middle value with the k. Okay? And then think about this index over here is the middle index. Okay? And we want to see whether k will actually exist in the input array. So there are basically two steps that we're going to keep doing. Number one, you want to access the middle of the current search space. The current search space, if you think about this entire array, I want to access the middle part. That's exactly what I do, right? That's step number one. You got to keep doing this. Step number two, once you get a middle value here, you're going to compare the value v against the one you're looking for. Okay? There are two cases. Well, there are three cases basically. I'll get to it. And then you want to compare the k you're looking for against the value v. So there are three possibilities. If k and v are just equal, we're done. We found it. K equals v, found. You can return. The other two cases, if k is less than v and also k is larger than v. So these are the two cases we got to worry. All right, so let's talk about each one of them. So let's say when k is actually equal to v, less than v. Okay. If k is less than v, we want to keep searching. Then k can only be in this half of the array, because all the values on here is guaranteed to be larger than or equal to v, because the array is somehow sorted, non-ascending. If you recall yourself about non-ascending, it's going to be flat or maybe arrays or like that, right? So whatever that's to the right of v in the array must be larger than or equal to v. So given that k is less than v, k cannot be here, no way. K's got to be here if it exists. Okay? So that's the first case. So that one there, I'm just going to write. Okay, so here I'm going to say something like k less than v. If k exists, k must be here. Be to the left of v. Must be in this particular search space, so I'll cut down that into half. Okay? Symmetrically, if I know that k is larger than v, then k cannot be here, because every value here is guaranteed to be less than or equal to v, because the array is sorted. Okay? I'm going to give the same comments here. So this will be the other case right here. Okay? So here I'm going to say if k exists. So k, if that's larger than v, if k exists, k must be to the right of v. Okay, let's now complete the recursion pattern. If k is less than v, you have to recur on the right. Sorry, on the left, beg your pardon. Recur on the left. Right here. Exactly what I mean by right, left, programmatically, I'm going to show to you very soon. Okay? And also, if that's larger than, you're going to recur on the right. Okay. So that's a basic idea about binary search. You got to make sure you understand why, when k is less than v, we can safely just go to the left half, given that the array is sorted, and vice versa. Okay. All right, any question about this? All right, if no, let's now go over one more page. For the remaining time, we want to go over the Java code. And to be in sync with the morning section, we're going to do the tracing on Tuesday and do some running time analysis. Right? I think it's going to be good. Okay. Let's look at this page here about binary search. The source code is also on the lecture site, which I suggest you play with it and try to test cases. Okay, let's go over very thoroughly. Okay. So the input here is really some sorted array. Okay, let me just make it thinner. Okay, array, it should be sorted. And this is the array that we're talking about, right? And then we talk about some value we're looking for, which is key. Okay, and later on, you're going to see that we're going to compare the key with the middle value. That's something you will see. Okay, and we're calling this recursive helper method binary search helper. You can see that's defined here. There's only two recursive calls we are making. Either we make the recursive call here, or we make the recursive call here. And one thing very important to see here, is it possible for both recursion to occur at the same time, or one after the other? Not really, right? Because you can see that what we're doing here is we say if we do this, else if we do this. So either recursive call can occur, not both. Look at the structure here, right? Watch out for that. And let's now see a little bit further. Let's see base cases. We got two base cases. So these are the two base cases. And this one goes back to the basic, right? When we first talk about recursion, about array. From larger than 2, that simply means we got empty range for the search space, in which case there's no way the element can exist. Empty set does not contain any member. That's why we return false. On the other hand, if the search space got exactly one element, in that way, simply check to see whether that particular element in the search space is matching the key. If it does match, then we simply return true. If it does not match, we return false. Right? So these are the two base cases for binary search, right? I'm assuming that you guys know about the basic, right? From the from and to, right? That's what we spoke about in the very beginning of the term. And then we talk about the recursive cases right here. Okay, recursive cases. So there are three cases over here. It's really about the three we talk about. Compare k, it can be equal to, less than, or larger than. Exactly that. Okay. So let's look at the else part. Else part means neither key is smaller, nor is it larger than the middle value. In that case, it will be equal to. In that case, we just return true. Okay, this one here tells us k is exactly equal to the middle value. That means return true. We found it. And then we, okay, here you got middle. You also got middle value. I just calculate the two values. So you can think about the middle is right here. And the middle value is stored right here in the middle index. So we're comparing K against it. So now you can see that in case number 1, if you remember when we say when we go to the left, right here, when K is exactly less than middle, K that we're looking for is exactly less than middle value. But we want to be very precise now in Java about what should be the range of indices to go from for this new search space. But I can see that visually quite easily, right? We still go from the from doesn't change. What about here? Exactly. Yeah, this one here is middle minus 1. If you see the diagram here, that's very obvious. Middle minus 1. All right? So that's why you saw here from to middle minus 1. Everything else stayed the same. We use call by value. And then symmetrically, if we know that, let's say K, when K is larger than middle value. So in this case, 2 doesn't change. But we're going to actually put the index right after the middle value. So after the middle, which will be n plus 1. Start from there. And then we're going to go in this way. You can see the middle value is exactly excluded. We don't need to check it anymore. So each search space guaranteed to be half, okay? Roughly half. So here you can see that, let me highlight it for you. Middle plus 1 and 2. Right here. All right, so that's about binary search in Java. Any question? All right, so I think just give me 2 minutes. I can recap very quickly, and then we'll continue on Tuesday. Give me 2 minutes, please, okay? I do owe you guys some time from last time. We didn't take a break. I'll give you that time back, okay? So we are now done with the binary search about the ideas over here. You want to review it. And also we talk about a Java code. You want to play around with the source code on the lecture site. Next Tuesday when we come back, we are basically going to look at some tracing over here. You guys can feel free to try to see how the range, the search space is going to change. And then we're going to do something challenging, which is to look at the Java code and see how we can come up with something called recurrence relation based on that. Once we get a recurrence relation, we're going to solve it manually there. That's something you guys will be expected to do. All right, thank you, and then I'll see you on Thursday.